Hi folks, it's time for section 12.2, the gas laws. Here's where it gets fun. And if you watch Hank Green at all, you know what a little bit of what we've got to look forward to. Going to have a few things that we have to keep track of with gases. And then we're going to show how these various, I don't know what they're called, conditions, how they're related to each other. First, we'll look at how each one's related to just one other one, and then we'll put it all together. We'll see how all these different people's, their work lends itself to one rule altogether. So, here's our objectives from your slides that you picked up in your envelope. We got Boyle's law, Charles' law, Gay-Lussac's law, and Avogadro's law. And you need to keep track of which guy's law what's being compared there. So for Boyle's law, it's pressure and volume. For Charles's law, it's volume and temperature. For Gay-Lussac's law, it is pressure and temperature. And for Avogadro's law, it has to do with the number of particles and these other values. So we'll actually get to the 22.4 liters per mole at STP. We'll get to how he came up with how much a mole is, all that cool stuff. I think it's pretty cool. And these things make, to me, they make an awful lot of sense. So let's get moving. I gotta make sure that I can move these slides along. So I gotta click on the slide itself. There we go. So this is a super important slide right here. I want you to make sure that you not only know what the thing stands for, but you're also going to need to know the units that we have to use to measure these things. Sometimes the problem will give you certain units and you've got to put them into other units first. So you got to know what those units are that we need to put things into. On the test, some people had a hard time using the units that were there, and so we had a lot of things in Celsius when really it's in kelvins. We can't make that mistake here because you can go negatives with Celsius, but you can't go negative with Kelvin. We have to use Kelvin when we're using proportions and things. You'll see why. So we got pressure, volume, temperature, and the number of moles. Pressure is going to be in atmospheres, ATMs, not in kilopascals or whatnot, I don't think. We might do some adjusting there. I know pressure's okay. We can use whatever one that we need because we'll never have a negative number there. Okay, so we can, pressure is interchangeable, but that problem will let you know. Volume, we're going to use liters so that, again, we have an absolute. We have a 0 at the bottom of it, and we can go up from there. Temperature, we're going to have to do it in kelvins. That one's very specific there. It has to be kelvins because Kelvin has a 0 and it goes up from there. And then the number of moles in the gas, N. Those are the important items for us to be balancing out and working with in our equations for gas laws. These are all the things that you can measure with gases. You can measure the pressure, you can measure the volume, how much space it takes up, like something like this. You can do it pretty exactly. You can say this one is 50 cc's. This is a big one. You wouldn't ever want to get a shot like this for sure. They'll tell you there's 50 cc's of air in the column here. You can measure the temperature of a gas. That's pretty easy. And then we're going to use STP and maybe some other quick tricks to measure how many things are in a certain amount of space. Okay. I'm going to switch over to the regular camera and show you a couple of things on the board because I kind of think we need two big ideas here to relate each of these laws and say which principle is actually in force. So I'm going to switch over to the main screen here. There we go. That wasn't too scary, was it? And I'm going to reintroduce you to a couple of, I think they're kind of basic algebra properties. This is what you did this in Algebra 1. Well, maybe you guys didn't because you were in summer school. I think it's, no, it's kind of toward the end. Anyway, Not mentioning names or nothing. Okay, so we've got two situations that have two pictures. We're going to have some things that relate to each other like this, and we call this direct variation. Something varies directly with something else, and then there's some constant, there's some multiplier there that tells you how those two things are related. A very easy example would be a unit conversion where we'd say 1 hour equals 60 minutes. So if we want to convert from hours to minutes, we have to use a 60 in there, right? We can see that if we put them together, we want to solve for the constant. Constant is going to be the ratio of one thing to another. That is, if the constant's like the number 12, and it needs to stay 12 the whole time. If A's value goes up, B's value has to go up as well. For instance, if we need to keep it at 12 to 1 to equal 12, if A goes up to 24, B has to go up to 2. So as one is increasing, the other one is increasing as well. That gives us a shape like this, tethered here at the point 0, 0, and then as one thing increases, so does the other. And the slope of this line is our constant. It's one way actually that we will do some physics labs where we're going to determine what that slope is so that we understand what the constant of proportionality happens to be. So this is another way of writing the same thing. This constant is a ratio of two things. If A goes up, B goes up. If A goes down, B goes down. Some of our gas laws are going to work that way. And maybe you want to think of those 4 things that were listed, the relationship between two things where if one goes up, the other one goes up. And the one that comes to my mind first is if the number of particles increases and the other things stay the same, like pressure stays the same, then the volume has to go up. Does that make sense? If we keep the pressure the same, if we're allowing the pressure to, the thing to like change in shape, if we add more things to something, then the volume will increase. Hang on, let me show you this. This, my friend, is a balloon. And it's got some pressure there when I put some air in it. And obviously if I put more air into it, it gets bigger, right? Still about the same squishiness, and but yeah, if N increases, then V has to increase. Okay, that's one of the principles that we got there. Okay, the other one is a curve that looks like this, and this is the inverse. This is, if we graphed it, we'd have y equals 1 over x. Remember that one? It's the like decay curve thing. It's the inverse x rule. And this says as something here increases, goes from 0 and goes up, the other value is dropping. They're inversely related. As one increases, the other one has to decrease. And that's because another way of writing this is k equals a times b. That the product of these two things has to stay the same. So again, let's just say that the constant for us needs to stay at 12. Like 12 times 1, okay? But maybe A drops to 6. That means B needs to go up. It needs to double in size to 2, so that 6 times 2 is still 12. Or if this one dropped to 3, this one has to go up to 4. Or some weird thing in between. I guess like we could have 4 and 3, right? So as one goes up, the other one has to go down. If it goes down, the other one has to go up, because the product of these two things has to be k. And you're going to see that in the book. We're going to have a curve there that's, I think it's Boyle's law. Yeah, pressure volume, and it'll be this kind. So we'll have, I think pressure is here. We're increasing the pressure, and if we increase the pressure, the volume goes down. I can demonstrate that pretty easily. I can pull this out on this plunger. Let's go to 50 cc's here. It's got 1 atmosphere of pressure in here, and I'm going to plug the top, and I'm going to jam this down as far as I can. I'm I have to push hard because I'm compressing that air down to 15 cc's. Then I can release it. I release the pressure. But let's see what happens if I push it down and then I let go. It's going to bounce back until it equalizes again down to where it was. So I'm decreasing the volume, and obviously I'm increasing the pressure. The pressure goes up, but the volume dropped down until I had 15/50ths, 3/10, 30% of the space. And so that means I've done a real good job there on increasing that pressure. I can actually calculate how much that pressure would have gone up. So you got one of these two, and that one is volume and pressure. Let's start with that. Okay, we'll start with that. And as we go through the slides, it's basically going to be either inverse variation, or the other one was direct variation. Inverse, one thing goes up, the other one goes down. Direct, they both go up or they both go down. Very straightforward concept. You got to get your brain wrapped around that so you can understand. And anyway, you can just kind of think of something like this. Or a hot air balloon. Hot air balloon. If you, let's see, heat up a certain volume of air, it wants to become more spread out and less dense, right? And so the thing rises. You heat it up, the particles move faster, they bump into the sides more, you get an increase in pressure with an increase of temperature. You also get a decrease in its density because it's trying to take up more space with the same number of particles. Okay, so I'm going to switch back to the other format here with the picture-in-picture thing, and let's go through some of those slides. Whoa, that was a little scary, wasn't it? Okay, so our first law is Boyle's law. Boyle's law is comparing volume and pressure. As the volume decreases, the concentration, therefore pressure, increases, and then vice versa. If the volume increases, then the pressure decreases. This, as it says, is an inverse relationship between pressure and volume known as Boyle's law. Boyle's law. For a fixed amount of gas at a constant temperature, the volume of the gas increases as the pressure of the gas decreases, and the volume of the gas decreases as the pressure of the gas increases. Okay, so I can do this too. I can put 10 cc's in here, and I can plug it, and then I can decrease the pressure by increasing the volume to 60. Okay, I'm creating a vacuum, and I'm gonna have a hickey on my finger here. When I release the pressure, then it goes back to where it was. I can take 10 cc's, 10 cubic centimeters, and increase that to 60 cubic centimeters. But what I've done in doing that is decrease the pressure quite a bit. It wants to go back to their more compressed setup. All right, I hope that makes sense. We will think about that as we think about in the car engine cylinder. I'll send you the link to his Smart Everyday thing where he shows you what goes on inside of a cylinder. Gas molecules get compressed, and then they're going to use a spark to cause it to expand. But there's only a certain amount of space in there if everything's closed up, if all the valves are sealed. So they squirt some gas in there, and then they compress it into a smaller space, but that increases the pressure. And then if you spark it and cause heat, then it's going to expand rapidly. So that's an example of how Boyle's law would work. So here's what you need to know. First, on the top, you've got our basic setup like we had here up on the board, that our constant equals the product of the pressure and the volume. The pressure and the volume, the product of those two things is a constant. Now, if you want to write it as before and after, like what are my conditions before? Maybe it's 50 cc's and 1 atmosphere. Pressure, volume. And then you change it so that you're at maybe 25 cc's. Now what's the pressure? You're going to do it as P1V1 equals P2V2. Or if you want to think of it, you got P at the start and volume at the start, and you got the pressure at the end of your experiment. That's where the 1s and 2s come from. Starts and finishes, or 1s and 2s. So in my case, I've got a 50 for my volume, and I've got a 1 for my pressure. 50 times 1 equals 50. If I decrease the volume to 25, my pressure has to go up to 2, so that 25 times 2 is still 50. That's Boyle's law. And so there, if you mark out the little dots there and you trace out a specific place where you can tell, like 600 for the volume in milliliters and 1 for the pressure, that's 60 times 1 is 600. You can go over to 300 and you'll find that 300 on the milliliters lines up with 2 on the pressure again. Then we still have 300 times 2 equals 600. That stays constant. The product of those two values stays constant. And there again is another pressure volume. But you better recognize that shape. That shape right there tells you this is an inverse relationship between the two of them. As you're going from left to right across the chart, the pressure is increasing, the volume is decreasing. As the pressure is increasing, the volume is decreasing. Volume versus pressure for a gas at constant temperature. That's what we're assuming with Boyle's law, that the temperature is staying the same. It follows that curve. Okay, sample problem then. We look at it, and as long as we're in milliliters and atmospheres, we're good. Our answer for the new volume is going to have to be in milliliters as well. So you collect your information, and you have to look at what's the initial situation and what's the final thing that I'm looking for. We start off with 523 milliliters. That's a volume. That's V1. And 1 atmosphere, that's P1. Pressure goes up, so P2 is 1.97. We're trying to solve for volume 2. What is the new volume of the gas? So you collect the information, and then you got to use the right setup. P1 V1 equals P2 V2. We're solving for V2, so P1 V1 over P2 equals V2. Now I said that fast, but we're just moving the parts around. You're on Algebra 2, you should be able to do that. 1 times 523 divided by 1.97 to 3 significant figures is 265. And then we use the units that we had in there for V1, and that would be milliliters. Okay, and that should make sense. I increased the pressure, almost doubled the pressure, so I should almost half the volume. Next one, temperature-volume relationship. Temperature-volume relationship is called the Charles's law. Jacques Charles's law. He discovered in 1787 that the gas's volume is directly proportional to the temperature. And here's the real kicker. We have to use the Kelvin scale. Again, we need an absolute. In our direct variation picture, we have to have the point 0, 0. On all these things, you got to have 0, 0 on there. So both the pressure, which one's this? Temperature and volume both have to have a 0 point, not a negative point. Okay, so we can't do temperature in Celsius here. We have to do temperature in kelvins. Heat a gas, it expands. Cool a gas, it contracts. And Hank Green showed that, where he took his can and he showed the differences in the, well, I guess it was actually pressure that was working there. But yeah, hot air balloon would be a good one for this. Heat it up, it should expand. Cool it down, it'll contract. When it expands, it becomes less dense and the balloon goes up. When it cools off, it starts to drop. Charles's law. Charles's law states that for a fixed amount of gas at a constant pressure, the volume of the gas increases as the temperature of the gas increases. So you see that one increases, the other one increases. One of them decreases, the other one decreases. So what kind of relationship is that? Is that direct or is that inverse? Well, you look in your book on page 427, and what kind of shape do you see? You're going to see this type of shape. And that tells you that that's direct. That's a direct relationship between the two things. So if one goes up, the other one goes up. We got kelvins, temperature on the bottom. We're heating it or cooling it. and then the volume is changing. I suppose we could do it the other way. If you change the volume really fast, you could actually cause something to heat up. It's harder to measure, though, I'll tell you that. So in terms of equations, here's what we're looking at. V over T equals K. Or if you want to write that a different way, you could say V equals the constant times temperature. Okay? You could rewrite that this way. V equals K times T. So if they write it the other way, V over T equals K, they're just saying if one of them goes up, the other one has to go up so that the ratio of those two numbers stays the same. Direct variation, temperature increases, the volume increases with it. If we're doing befores and afters, we're like V1 over T1 equals V2 over T2. It has to be the ratio of the initial conditions equals the ratio of the final conditions. And in this one, we are keeping the pressure the same. We're allowing the thing to expand. We're not doing it in a fixed sized container. So you see there's the condition at constant pressure. We're allowing it to expand and contract without the pressure changing. What slide is this? 50? Okay, 51. All right, so that's the kind of picture that you're going to get, or this type of picture right here. And again, if you go to any of these points, like you go to 0.4 and 200, the ratio of 200 divided by 0.4 is going to be the same as if you went here and compared whatever that temperature would be to whatever that volume would be. It should be the same ratio of those two things. We get a straight line relationship between the two, between those two factors. Sample problem really quickly. We're going to gather some information, but there is a little trick to this one. And do you see it? And the problem is we've got Celsius involved here, and we're not allowed to use Celsius here because we have a positive and we have a negative. And that doesn't work that way with ratios. We have to have an absolute. We have to have the lowest number that we can have on our picture is 0 for temperature. We can't have negative. So we got to switch both of those into kelvins by adding 273. So as we gather our information, we've got an initial volume and initial temperatures. And then who's coming? Is that Dutch? And we've got to switch both of those to kelvins before we proceed. It is. Hang on. All right. So here we go. You know, both the temperatures get shifted up 273, so now we're all in the positives. Have to all be in the positives on these types of problems. I'm going to say this like 18 times. Kelvins, positive numbers. And we got to just figure out what we're solving for. We're solving for V2. So let's move. We can either do it this way and just do the math, or you can do V1 over T1 and then multiply by T2. T2 V1 over T1 equals V2. How do you like that? Plug the numbers in. Double check what kind of units you ought to have. Look at the answer and see if it makes sense. Okay, what do we got here? Sorry, I had some Pepsi. P for Pepsi. Volume 1 was big, temperature 1, and then we dropped the temperature. And then, go ahead. I don't know. He was here. Anyway, so the temperature drops, so the volume should drop as well. If you get an answer that's bigger than 665, or you get an answer that's negative, you definitely did something wrong. Definitely did something wrong. And you should think about that a little bit. All right. Next slide. Temperature, pressure. Have we done that one yet? No, yeah, that's what we were just doing, right? Directly proportional relationship. All right, so that's what the picture will look like here with pressure and temperature. Gas pressure is directly proportional to Kelvin temperature at a constant volume. Now we're not letting the volume change. Now we are heating something up in a closed container and the pressure is going to build like in a boiler or something like that. But look at that line again, straight line, and it's tethered to the point 0, 0. So we got to be in kelvins, and we're in pressure. In this case, it's in atmospheres this time. This is Gay-Lussac's law, or you probably say it Guy, because he's French. Gay-Lussac. I don't know how to say it. I don't know how to say anything in French except for like parlez-vous français and you know, lieutenant and stuff like that. Whatever. Okay, so now the relationship is temperature and pressure, and you can see from the equation P equals K times T. Pressure varies directly as temperature does. Again, remember what that means. The ratio of these two things, if one goes up, the other one has to go up so that the ratio stays constant. If they both go down, they got to go down together. You cool something down, the pressure goes down. And if you heat something up, the pressure goes up. So you can either do it as the ratio of pressure to temperature is a constant, or you do the before and after, P1 over T1 equals P2 over T2. The initial conditions and then the final conditions. If pressure goes up, temperature goes up. If pressure goes down, temperature goes down. And so we get this type of picture. You see that line again. It's like it's one or the other, right? It's either direct or it's inverse variation. So brief here again, we've got a problem because we've got degrees Celsius. We can't have that. We got to have an absolute temperature scale, so we need kelvins. But we've got an initial pressure of 101 kilopascals, which is standard atmospheric pressure. And then 22 degrees Celsius is kind of room temperature-ish. And we go up to 55 Celsius, but both of these got to have 273 added to them so that they're on an absolute Kelvin scale. So as we gather our information, pressure 1 is 101. We're looking for pressure 2, and we got to add 273 to both temperatures to get 295 for our initial temperature and 328 for our final temperature. So we're heating it. The pressure better go up. You better get an answer that's bigger. We're keeping the volume the same this time. We're not letting it expand freely. We're holding it in a container and we're heating that thing up. So, you know, they always say with like a thing of spray paint or a can of something, they say, do not throw in the fire. And you're like, why would I do that? And they're like, because it might explode. And you're like, ooh, that sounds like fun. Pressure will go up until the container can't hold it anymore, and then there'll be a change in volume. And you don't want to be around when that happens. Okay, last guy, Amedeo Avogadro. Remember, he kind of looks like a house elf. In 1811, it proposed the idea that equal volumes of all gases under the same conditions have the same number of particles. This was like, to me, I just think like, how did he figure that out? It just totally blows my brain. And of course, he gets that Avogadro's number named after him, which you've got on your calculator. But gases was the thing that helped us figure out how stoichiometry works. I know you're really excited about stoichiometry, but you all figured it out. So let's just, you know, call that a victory. The result of this relationship is that molecular masses can be easily determined. And it's brilliant. If we're at SDP, all we need to know for how many particles there are is to measure the volume. And gases volume is not so hard to measure. It's the number of things that's hard to measure. But now we got to go between here. Stanislao Cannizzaro used Avogadro's principle to determine the true formula of several gaseous compounds. He's like, wait, carbon dioxide is CO2 and oxygen is O2, not just O. And now we can write formulas for things where before we couldn't do that. It all started with gases, folks. So this is called Avogadro's law. Avogadro's law states that the equal volumes of gases at the same temperature and pressure, that would be SDP, at 0 Celsius and at 1 atmosphere, contain equal number of molecules. With this knowledge, chemists gain insight into the formula of chemical compounds for the first time. It doesn't mean the densities are not the same. They're probably not the same, but it means that the same amount of particles are in the same space. Super important. And then as we look at the formula for this, we see that V equals K times N, N for number of moles. This is direct relationship. So what type of picture should we see? Should we see the curve or should we see the straight line? Well, direct proportionality means straight line. So you need to make sure that this is one thing I want you to have memorized. Memorized. And that would be this number right here, 22.41 liters of any gas at STP is 1 mole of that gas. Therefore, this is the most important sentence on this page here. And that if we're at STP, which means 0 Celsius and 1 atmosphere, the mass of 22.41 liters of a gas, that's 1 mole of a gas, at 0 Celsius and 1 atmosphere will be equal to the gas's molecular mass. Brilliant! Brilliant! Way to go, Avogadro! You are my hero. There's Avogadro's law and principle. Oxygen, carbon dioxide, hydrogen, they're all different sizes, but if you have a mole of those things, they will take up the same amount of space, same volume, but bigger ones are more dense. And so this makes sense that hydrogen is super small. So you put smaller things, the same number of small things in there, they're going to be a little bit further apart, which means it's less dense. And then you get, what would come next? I guess oxygen would come next, and then carbon dioxide. So think about when they talk about, I guess when there's a fire or something like that, and gas is rising, and gas is like, where's the gases, they're going to sink, right? Or in a room that's filling up with carbon dioxide, where do you want to be? Carbon dioxide is more dense, I believe. Carbon and 2 oxides. Yeah, oxygen will stay higher up. You want to try to get as high as you can in a room that's filling up with carbon dioxide. And then you know that hydrogen balloons, they go up. They go up. So keep that in mind the next time you're playing around with balloons. Everybody loves balloons, right? Okay, so I'm going to leave you with a few problems to do, practice problems. You get the right ratio. Make sure that if anything has temperature in it, you're putting it into kelvins first. And then please think about whether or not your answers are sensible or not. Should the answer be bigger? Should the answer be smaller? My answer is negative. Does that make sense or not? You should look and see if it's direct or if it's inverse variation. Very straightforward concept, but sometimes you just got to put your thinking cap on. Put your thinking cap on and work it through in your head and ask if something's reasonable or not. There you go. We'll send you the rest of the instructions that you need and links to other videos in the email. Thanks for tuning in.